Four astronauts are sitting in quarantine right now at Kennedy Space Center in Florida. Bags packed, suits ready, waiting for the weather to cooperate. SpaceX Crew 12 is almost go, and the countdown is very much on.
Meanwhile, our sun is doing what it does best, putting on a show. Plus, a lava tunnel the size of a city has just been confirmed under the clouds of Venus. And a tiny teaspoon of asteroid dust has just rewritten the story of how life's ingredients form in space. Good morning, good evening, wherever you are in the world, and welcome to Astronomy Daily.
I'm Anna.
And I'm Avery. Let's get into it.
Let's kick things off with our lead story, because the ISS is short-handed right now, and NASA wants to fix that as soon as possible. The SpaceX Crew 12 mission has been pushed back once again. This time to no earlier than Thursday, February 12th at 5:38 in the morning Eastern Time. The culprit? Weather along the Crew Dragon's flight path.
Yeah, mission teams did a weather review and decided to waive off the Wednesday window entirely. Conditions are expected to improve Thursday, but Friday the 13th is also being kept as a backup. So we're in a holding pattern, but a short one, hopefully.
And while we're waiting, let's talk about the crew, because this is a really international team. Commanding the mission is NASA astronaut Jack Hathaway, his first spaceflight command. Pilot seat goes to the brilliant Jessica Meyer, who's no stranger to the ISS. Then you've got Sophie Adenaude, representing the European Space Agency. This is her first spaceflight. And Roscosmos cosmonaut Andrei Fedyev completing the quartet.
They'll be riding aboard Crew Dragon Freedom, which is itself a fascinating spacecraft. This will be Freedom's fifth flight, returning after a whopping 501-day turnaround since Crew 9. And here's something to watch for at launch. This mission will mark the very first use of Landing Zone 40, a brand new landing pad built right inside the SLC-40 complex itself. So the booster is going to launch and then come back and land right next door. That's wild.
It is wild. Now, one thing that makes this particular rotation different from the usual 6 months is the expected duration. Because of Crew 11's early medical evacuation back in January, Crew 12 is expected to stay for 8 to 9 months, longer than a typical stay. The ISS needs the staffing, and this crew is ready.
And it's a big week for launches beyond just Crew 12. The launch manifest is absolutely stacked right now. We have ULA's Vulcan rocket going up with USSF-87, a pair of satellite surveillance for the U.S. Space Force. Then there's the first Ariane 6-4 launch, which will carry 32 Amazon Kuiper internet satellites. That's Starlink's main competitor, by the way. Plus a Russian Proton-M and, surprise, surprise, multiple Starlink missions. It is genuinely one of the busiest launch weeks we've seen in a while.
So if you're a launch watcher, clear your Thursday calendar. Live streams will be available online for most, if not all, of these launches.
Okay, story 2, and we keep an eye on our star because right now, as we reported a few days ago, it is being very talkative. Sunspot region AR 4366 has been one of the most active regions of solar cycle 25. And overnight, it fired off 4 M-class flares. The biggest was an M2.8. That's a moderate flare for context at around 2:14 UTC this morning, which triggered a minor R1 class radio blackout over the seas between Australia and Papua New Guinea.
Just to give people a quick refresher on the scale here, solar flares are classified by their peak X-ray intensity. C-class are minor, M-class are moderate and can cause brief radio blackouts at high latitudes, and X-class are the big ones, the kind that can knock out power grids and satellite communications. So 4 M-class flares in a day is definitely worth paying attention to.
ARC 4366 has actually been the source of some spectacular X-class activity over the past couple of weeks too. It's been a busy region. Now it's rotating out of the Earth-facing part of the sun, so today the forecast is quiet to unsettled as the coronal hole stream influence gradually weakens. But forecasters will be watching it closely. If we get any significant CMEs thrown our way, that could mean auroras pushing further from the poles than usual, which is always exciting news for skywatchers.
We're still in an active phase of solar cycle 25, which is tracking hotter than predicted, so don't put the Aurora alert apps away just yet. We'll keep monitoring.
We certainly will. This is exciting stuff.
Okay, moving on, story 3 takes us to one of the most exciting ongoing areas of science, the Bennu samples from NASA's OSIRIS-REx mission. We've talked about Bennu a lot, and each new study seems to shift our thinking a little more. This week's paper, published in the Proceedings of the National Academy of Sciences, might be the biggest shift yet.
So what's the finding? For decades, scientists thought amino acids in asteroids form through what's called Strecker synthesis, a process that requires warm liquid water. The classic picture was something like a wet, warm asteroid interior, chemistry bubbling along. But the Penn State team, led by Alison Basinski, looked at the isotopic signatures of amino acids in the Bennu samples, specifically glycine, which is the simplest amino acid, and found that the story is much more complicated.
The data suggests these amino acids formed under harsh, cold, icy, radiation-rich environments, the kind of environment we'd associate more with the outer solar system than a warm, watery asteroid. Basinski described it as their results flipping the script on how amino acids form. It's not just one pathway anymore. It looks like there are many conditions under which life's building blocks can emerge.
And why does that matter? Because if amino acids can form in extreme icy environments, not just warm, watery ones, the range of places in the cosmos where life's precursors might exist just got dramatically wider. We're talking about icy moons, comet nuclei, the outer reaches of the solar system, places we might not have been prioritizing in the search for life's ingredients.
What's remarkable is that all of this came from a sample smaller than a teaspoon. That speck of 4.6 billion-year-old asteroid dust is genuinely changing our understanding of how life may have gotten started. The OSIRIS-REx mission just keeps on giving.
Story for today, and I genuinely love this one. We found lava tubes on the moon, we found them on Mars, and now, for the first time, scientists have confirmed one on Venus. A team from the University of Trento in Italy has published the paper in Nature Communications this week, revealing the existence of a massive underground lava tunnel on our closest planetary neighbor.
And the really clever part of this story is how they found it. Venus is famously difficult to observe. It's permanently wrapped in thick sulfuric acid clouds that block direct photography of the surface. So the team went back to radar data collected by NASA's Magellan spacecraft between 1990 and 1992, data that's over 30 years old. They developed a new imaging technique specifically designed to detect underground conduits near surface collapse features called skylights, and when they applied it to the Nix Mons region, named for the Greek goddess of the night, they found it.
Now let's talk size for a moment, because this thing is enormous. The lava tube is estimated to be around 1 kilometer wide. That's wider than any lava tube found on Earth, the Moon, or Mars. The roof is at least 150 meters thick, the empty void below is at least 375 meters deep, and based on the surrounding terrain analysis, the whole conduit could extend for at least 45 kilometers underground.
45 kilometers. That's a subterranean highway. And there's an interesting reason it's so big. Venus has lower gravity than Earth and a denser atmosphere, which actually favors the rapid formation of a thick insulating crust on top of lava flows. So the tubes can grow larger and last longer on Venus than elsewhere. The planet with the worst surface conditions in the solar system might have some remarkably stable real estate underground.
This also has really important implications for future Venus missions. ESA's Envision spacecraft and NASA's Veritas are both being developed for Venus, and both will carry advanced radar systems capable of doing this kind of subsurface analysis in far greater detail. The team describes this discovery as only the beginning of what could be a long and fascinating research program into Venus's hidden geology.
And our final story today takes a delightfully unexpected angle on the search for extraterrestrial intelligence. A new paper in the International Journal of Astrobiology by plant biologist Lincoln Tice at UC Santa Cruz argues that if we want to find advanced alien civilizations, we should be looking for exoplanets with large, accessible deposits of coal.
Coal. Not radio signals, not Dyson spheres. Coal. I genuinely love this. So what's the argument? TICE traces the chain of development that led to us being able to communicate across interstellar distances. On Earth, none of our advanced technology, no steel, no deep fossil fuel extraction, no electricity, no radio telescopes, would have been possible without first being able to forge steel. And steel required coal. Specifically, huge amounts of shallow, energy-dense coal, like the deposits laid down during the Carboniferous and Permian periods, roughly 330 to 260 million years ago.
The paper argues that the same logic should apply to any technological civilization anywhere in the universe. Intelligence isn't enough. Biology isn't enough. You need the geology to match. A planet that happened to grow the right kinds of forests at the right time in its history under the right conditions to bury them and compress them into energy-dense coal seams that a curious civilization could then dig up and use to bootstrap an industrial revolution.
And the implications for SETI are fascinating. The paper suggests planets in the so-called photosynthetic habitable zone, where both liquid water and oxygen-producing photosynthesis are possible, might be relatively rare. Even rarer are the planets where all the conditions align: the right star, the right orbit, the right biology, the right geology, and the right timing. Coal doesn't just appear. It requires a very specific sequence of events across hundreds of millions of years.
There is also a potential detection angle. An alien industrial revolution would produce atmospheric signatures, elevated carbon dioxide, sulfur dioxide, nitrogen oxides, soot. These are theoretically detectable with sufficiently powerful telescopes. The catch, as the paper acknowledges, is that the coal-burning phase of any civilization would be relatively brief. We certainly hope it is. So the detection window would be narrow, but it adds a whole new layer to what we're looking for when we study exoplanet atmospheres.
It's also a slightly humbling thought. The reason we can have this conversation, the reason we built the telescopes and the rockets and the radio transmitters, might ultimately come down to a lucky geological accident 300 million years ago. We happen to live on a planet with a lot of coal in the right places at the right time. Not every world will be so fortunate.
And that is your Astronomy Daily for Tuesday, the 10th of February, 2026. From solar fireworks and a countdown to launch to lava tunnels on Venus, rewritten science from Bennu, and a genuinely thought-provoking new take on the search for extraterrestrial life. It's been quite the episode.
If you enjoyed today's show, please take a moment to leave us a review wherever you listen. It genuinely helps more people find us. And if you want to go deeper on any of today's stories, we have links to all the source articles waiting for you in the show notes at astronomydaily.io.
Find us on social media at AstroDailyPod. And if you've got a question, a story tip, or just want to tell us what you think, we'd love to hear from you. Thanks for listening, and we'll see you again tomorrow. I'm Anna.
And I'm Avery. Keep looking up.